Okay, our last example in chapter 9 of using the vertex. So I call this timed kick. You could call it hang time. It's exactly that though. Say you kick a ball, it disappears above the horizon. You can't see how high it got. If you're interested, send me an email. I've got lots of videos of this with classes. We've gone out on the field. We've kicked balls. We've timed it. We've made videos. All sorts of good stuff. So this really is what it says. We're kicking a ball. We want to see how high it gets. To do that, we need a formula, and that formula is based on the strength of gravity at the surface of Earth. So here is our formula. And notice that I've written this formula in function notation. So that h of t, and I did say that correctly, it sounds like multiplication, but it's basically saying what is h for this value of t. That h is chosen for the height, t is chosen for the time in seconds. Now, there's lots of ways of computing negative 16. It's the acceleration due to gravity. It's related to the acceleration due to gravity at the surface of Earth. It actually comes from a calculus equation. You can derive it, and we do that in class when we have the time to do that. So there's our negative 16. That comes from the fact that we're on a nice sized planet. We've also got our v sub 0. That may be new notation to you, the idea of putting subscript. Now v is velocity, and we've talked about velocity all semester. Velocity is just the speed. But the speed of this ball, and you can imagine anything thrown or kicked or launched or thrown out of a trebuchet or anything like that, its speed decreases as gravity is pulling it downwards, and then its speed decreases downwards as it returns to Earth. So that v sub 0 is not all the speeds. It's not a variable. It's the initial speed, the speed at time 0. So v sub 0, some people in sciences and some of my colleagues in math will say v naught, where that naught is referring to the 0. And similarly, we've got lots of heights. This thing goes up and then it comes down. But we've also got h sub 0, h naught. And that's the height at time 0, the height at which you start the stopwatch when you're timing the flight of this ball. So there's our equation. There's a lot in it, and we've got a lot of work to do. So let's take a look at the setup of this question. A ball was kicked from a height of 3.3 feet. So let's deal with the 3.3 feet first. That was the height it was kicked from. So that's actually the initial height. So h sub 0 is 3.3 in this particular example. It was in flight for 1.8 seconds. Now, this is an extraordinary thing. Take a look at how we write that. That actually tells us two pieces of information. It tells us that after 1.8 seconds, the height returns to 0. So this is kind of your first test of being able to interpret function notation. H of 1.8 is 0. What's that saying is that the height after 1.8 seconds is 0. That's two pieces of information. T is 1.8, H is 0. So a lot is going on in that relatively short sentence. It was in flight for 1.8 seconds. H of 1.8 is 0. We're going to need that information. Now, we can take our general equation for the flight of anything that's kicked or launched, basically anything that's not propelled on its own, just given some initial momentum and then it returns to Earth. We're going to take that equation and we're going to plug in h sub 0, that 3.3. So you're going to see exactly the same general equation. The only thing that will have changed is that h sub 0 becomes 3.3. So here it is, just a little change right there at the beginning. Now, there's still too many unknowns, h, t, and v sub 0. So the first thing we've got to do is find how fast that ball was kicked. Now that's an extraordinary kind of thing to realize, that you can compute just from timing how long a ball was in flight before it hit the ground. And that is how fast it was kicked. And that's actually the first question we're going to answer. And we're going to do that with algebra, a little arithmetic. And we're going to use the fact that it was in flight for 1.8 seconds. Remember, that's telling us two pieces of information. So let's say what happened after 1.8 seconds. So notice all the t's have become 1.8s. So if that looks like substitution to you, you are exactly right. That is substitution. 1.8 is taking the place of t. Everything else is the same. Now, you might say, okay, fine, t became 1.8, but remember that after 1.8 seconds, the height is 0 again. So in this next step, I'm going to do two things. I'm going to do a lot of arithmetic, but take a look at the left side. Take a look at what happened over there. That 1.8, when we plugged it in for the height, became 0. Now that makes sense. The height after 1.8 seconds is 0. Now the other thing that happened, of course, is a bunch of arithmetic. Now, what does that mean? That means we multiplied negative 16 times 1.8 squared, and we added 3.3 to it. So you do that arithmetic almost certainly in your calculator, and you get negative 48.54. The other thing that I've done is cleaned up how we're showing the multiplication here. There's no reason to show the coefficient after. That looks confusing to me. So I rewrote that term with the v sub 0 in it with the coefficient first. So there's 1.8 v sub 0. Now this is a linear equation. All we have to do is get the v sub 0 by itself, and there's only two things that have to go. We have to get rid of the constant term as we work backwards through the order of operations, and then we have to get rid of the coefficient. So I'm going to do exactly that. I'm going to add 48.54 to both sides, and then I'm going to divide both sides by 1.8. So amazingly, just by timing how long this was in flight, we know that it was kicked at 26.97, let's say about 27 feet per second. So we know the speed it was kicked at. We should say that this is the instantaneous vertical velocity. This is only the component going straight up and down. We rarely kick balls straight up in the air. So there's also a horizontal component, but that's not important for this course. What I'll be asking you is the initial vertical velocity, just that vertical component. That's what I'm going to call v sub 0. So our v sub 0 is, well, 26.97. And if you're wondering about that 26.97, I'm showing this in exactly the same way that I do in my open math. That is rounded to the nearest hundredth. So whereas I usually say leave the exact value on your calculator, here you're going to have to clear it. When we use v sub 0 again, when we use the initial vertical velocity again, we're going to have to enter 26.97. Now we're doing good. And what do I mean by that? We've now taken an equation that had three variables in it, ht and v sub 0, and we've now gotten rid of one of them. We know exactly what v sub 0 is. It's 26.97. So our equation is now down to two variables. Time is telling us height. So you can plug in any time you like here. If you get a negative height, it means that you've exceeded the flight of the ball. If you get something in between, you're talking about where it is up in the air. We're interested in finding where it reaches its maximum height. That's a vertex question. So negative b over 2a. Remember, our b was our initial vertical velocity. There it is once we've changed its sign. And amazingly, in the denominator, we've got the acceleration due to gravity, 2 times negative 16. So we do a little arithmetic, and we learn that it reaches its highest point after 0.84 seconds. And again, I've rounded to the nearest hundredth. You're going to be asked to do the same thing in my open math. So 0.84 seconds, it reaches its maximum point. Now that's all very well and good, but remember what this question was. It said, what is that maximum point? How high does it get? Now we've got an equation for that. We just found the velocity, so we're going to plug it in. And I'm going to use function notation again. So here is the height after 0.84 seconds. So wherever we see a t, we substitute in 0.84, and we get a lot of arithmetic. Notice that's entirely arithmetic. The only thing going on there is arithmetic. So we put it in a calculator, and out pops, after we've rounded, 14.67. Again, we're rounding to the nearest hundredths. So there's the maximum height. This got to about 14.5 feet, and that's as high as it got. Okay, one more of these timed kick questions. They are pretty cool to think that without a lot of information, we're able to figure out how fast it was kicked upwards, when it reached its maximum height, and what its maximum height was. When we take a look at this question, we notice that it's very similar. It says that a ball was kicked from a height of 2.3 feet. That's going to tell us our h sub 0. It was in flight for 4.5 seconds. Well, that's going to tell us that after 4.5 seconds, its height returned to 0 again. So we're going to go through exactly the same steps again. So taking that generic equation, we substituted in h sub 0, that initial height, the height it was kicked from. And then we're going to substitute in what we know about the length of its flight. That is, we're going to ask the question, what happened after 4.5 seconds? So notice that t is now 4.5, so all sorts of good substitution took place. T is becoming 4.5. And that includes in the function notation itself, h of 4.5, that is the height after 4.5 seconds. And we know what the height after 4.5 seconds is. It's 0. So that left side is about to become 0. The right side, yep, out comes your calculator because you've got to do a fair amount of arithmetic over there. Take a second to do this. It's amazing how often students forget how to enter something in their calculator correctly. So make sure that you can get that negative 321.7 as the constant term. Now we're working backwards through the order of operations. We want to get the v sub 0 by itself. So as we work backwards through the order of operations, we're going to undo that subtraction. No great surprise. We're going to add 321.7 to both sides. To get the initial vertical velocity by itself, we're going to divide by the 4.5. So there's, and of course it's rounded to the nearest hundredth. So there's our initial vertical velocity, 71.5 feet per second. This probably was propelled. That's really fast. 1 second, 71.5 feet. I'm doubting this was kicked, but in some way it was propelled vertically upward. Now, 4.5 seconds does not sound like a long time, but in terms of something falling and being propelled upwards, it really is. So the next part of this question is finding where that vertex is. So we take our equation, the one we were working with a few seconds ago, and we say, hey, we know what v sub 0 is now. So when we recopy the formula for the height of this particular ball, we put in the 71.49, taking the place of v sub 0. Now we're going to say, well, when, meaning what time, did it reach that vertex? And of course, negative b over 2a is going to answer that question. There's negative b, and in the denominator, the acceleration due to gravity at the surface of Earth, approximately. And it looks like we get 2.23 seconds, again, rounded to the nearest hundredth. So after 2.23 seconds, this ball, whatever's being projected, reaches its maximum height. Now we know everything about this equation for this particular ball, so we're going to say what's the height after 2.23 seconds, which means we're going to plug in 2.23 wherever we had a t. Notice that there are no variables over there. This is a job for your calculator, and it looks like I got an answer of 82.16 feet. Remember, rounded to the nearest hundredth.